Okay, thank you very much for the permission. Welcome back again to noise class. Hopefully none of you is involved with the flood. Anyone involved? It's okay if you have problems with uh, flood, you need some help, let the school knows so that we can relay some help to you. Okay, don't keep it to yourself. Anyway, let's move on with noise. Um, we have talked a little bit about room acoustics and about absorptions and so on. And now we want to see how we can use our understanding related to sound transmission in the partition with calculating the sound pressure level uh, in rooms when we have partition in between. So for example, if we have two rooms like this, okay, uh, in the first room, whereby we have our sound source, the sound pressure level is given by L1, and then adjacent to this room we have a partition, okay, and this sound will be reflected and also transmitted through the partition to the next room or to the adjacent room. And due to this original sound in room 1, we will have sound pressure level at room 2 given by L2. Okay, so the sound pressure level at room 2 will depends on the amount of absorption in room 2 as well as the characteristic of the partition itself that is passing through the noise to room 2. Okay, so normally we will be calculating what we call as sound transmission loss given by uh, this R here. Okay, this is our sound transmission loss. Right, it is equals to L1, the original sound pressure level, minus L2 plus 10 log 10 SP is the surface area of the partition divided by A2, which represents the absorption within the receiving room. All right, and since we know that absorption is dependent on frequency, the sound transmission loss is also frequency dependent actually. Okay, in some standards we are measuring at different frequency value. It can be at 16 different frequency values if we are using 1/3 octave interval, and that frequency is between 100 hertz to 3150 hertz. Okay, that's also possible in some standards. In some initial calculation, we might just use one single value to simplify our life. For example, we are taking at 500 hertz. That's also possible. Okay, so at the end of the day, it depends on the standards of measurement that we are following. We can rearrange this guy, this sound transmission loss equation, to calculate what would be the sound pressure level at the receiving room L2. Okay, and to be frank with you, this value of L2 is the average value of sound pressure level. Uh, in a room, you'll have certain area that will have different sound pressure level compared to other area. It depends on the room arrangement as well. But we are talking about average value here. We are assuming that after some time, the sound pressure level will diffuse and will be at a steady state level. Okay, so this L2 is an average overall level in the receiving room. So it is equal to original sound pressure level at the transmitting room minus sound transmission loss R plus 10 of 10 uh, SP. This represent the sound or noise radiation by the partition. Okay, so this the amount of noise being transmitted by the partition, and then we have plus 10 of 10 1 over 8 2 here. This represent the absorption or the correcting factor at the receiving room. So if this value is large, if the receiving room has a large absorption value, so the sound pressure level will drop as well. Okay, so for simplicity, we can also do a quick approximation. Okay, this will depends on the parameters of the partition itself. If we know the dimension of the partition, the material of the partition, uh, normally we'll have spec sheets for this material, so we can calculate what will be the uh, sound tension index or sound transmission loss for the partition. Okay, so straight away we know the sound pressure level at the receiving room is equals to the sound pressure level at the transmitting room minus this sound tension index or sound transmission loss. Okay, both of them are the same, and I might use them uh, interchangeably. Okay, so L2 equals to L1 minus R. This is for fast approximation. Of course, this will give you the highest sound pressure level. Okay, since we uh, so it will give you a quick approximation, okay, of the sound pressure level. But if we want something more exact, we have to consider the additional transmission by the partition as well as the absorption by the receiving room. So for example, we have something like this. We have an office, a foreman office located next to a workshop, and we're told that the workshop has a reverberant sound pressure level at 72 dB. Reverberant means it's a constant sound pressure level in this particular room or in this particular workshop. And we were told that the office has a wall made of demountable metal construction with average transmission loss of 35 dB. Okay, so what would be the reverberant sound pressure level or the average sound pressure level within the office? And we were told the office dimension is 4 meter length times 3 meter width times 2.5 meter height. Okay, and the 4 meter length wall is the common partition or the common party wall between the office and the workshop. Okay, so what you need to do initially is to determine how large is the partition. Okay, so you have your office and workshop. Okay, the dimension of the workshop is unknown, but we do know the sound pressure level within this workshop, 72 dB. Okay, we know between the office and the workshop there's a partition, right? So the office has a dimension of 4 meter times 3 meter times 2.5 meter height. Okay, so there's no question about the height. So it's vertical 2.5 meter. As for the length and width, it depends. In this case, we were told that the common partition is made up of 4 meter length wall. So this is our partition, and this length should be 4 meter. Right? So that means this length should be equals to 3 meter based on the information given about the office dimension. Alright, so our wall has a dimension of 4 times 2.5 meter. Okay, so this is our partition. Alright, so you should be able to get this from the text given in question. Alright. We were told that average absorption coefficient or alpha bar is equals to 0.1 for the office. Alright, so our equation is this guy here. Sometimes I use R, sometimes I use TL. Transmission loss is the same thing. I just like to play with your brain a little bit, tease you. Okay, in some instances it's called sound reduction index R. In some instances it's called transmission loss for the partition. Both of them are the same thing. Okay, so L2 is equal to L1 minus CL plus 10 log 10 SP plus 10 log 10 1 over A2. Okay, so based on the information given, you can calculate what will be the surface area, the exposed surface area of the room. Okay, so in this case it's not any room, it's the office, and then calculate what will be the volume of the office. The absorption in the office is equal to exposed surface area in the office times the average absorption, also 5.9. This one here, okay. And then we have room collection, which is equal to 10 log 10 1 over A. So we have minus 7.71 dB. And then we have the partition area equals to 4 times 2.5, which is equal to 10 meters squared. This is our SP previously. Okay, so the contribution or the noise transmitted by the partition is equal to 10 log 10 SP equals to 10 dB. So the reference of pressure level, or L2, okay, in the office is equal to L1 minus the transmission loss plus this guy here, okay, which is the partition contribution plus the room correction. Right? So this is our reference submersion level in the office. And if we do quick approximation, which means we are using just the transmission loss for the partition, L2 will be equal to L1 72 minus 35, which is equal to 67 dB. So the value of quick approximation is about the same as the calculation using this equation, which consider the contribution coming from the partition as well as the absorption within the room. Alright. For sound insulation, basically the idea is we want to stop the sound, right? And to stop the sound, one of the biggest factor that could help us is weight. Okay? If we have something that's heavy, we can stop more sound compared to something that's light, which makes sense. If we have a partition or a wall that is very light, since it is light, it is also vibrating. That means it is helping in transmitting the sound. But if the partition is very thick and heavy, okay, it's very difficult to vibrate. So it will insulate sound more, okay, compared to a lightweight partition. And of course, to insulate, we have to ensure that everything is homogeneous as possible. Okay, because if there is certain area within the partition that is not effective in insulating sound, so the sound will transmit through that area. We can also affect sound insulation by changing the stiffness of the partition as well. And as before, we want to avoid any discontinuity as much as possible, okay, to ensure that we have a good sound insulation. So in general, for weight, increasing weight will increase sound insulation. So as a rule of thumb, each doubling of weight will increase the sound insulation by 5 dB. Okay, so if we have something that is complex, sometimes adding weight is quite difficult. Okay, so we have to play around with the arrangement of the material within the partition as well. Alright, but if we can use something that's heavy, that will help us a lot. Okay, unfortunately, most of the time it is very difficult to add something that's heavy in the design, especially when everything has been fabricated. We can make provision for heavy materials for the partition most of the time only within the design stage. If we pass this design stage, everything has been constructed, suggesting to put heavy material to reduce vibration or reduce noise at the partition might not be acceptable, okay, or even practical to begin with. Okay, so there's no I would say one-to-one substitution for weight. Uh, it's I would say not possible to have something that's very lightweight, but at the same time, it's very good at absorbing sound. Okay, Um, Normally, we can insulate at the best possible way by ensuring that our partition is homogeneous. Okay, so everything is covered. If we have any holes, just like what we have discussed earlier, mind the gap, it will degrade the performance of the partition a lot. Okay, so imagine uh, a very small gap at the hole, okay, could reduce the performance of our partition. Okay? So let's say we have 1 millimeter gap, 1 millimeter only, along 10 by 10 meter panel. That alone, which uh, equals to 0.01% of the partition area, will drop the performance of our partition to a maximum value of 40 dB. Right? So that's the effect of the gap or hole on the partition is very detrimental. Okay, so avoid hole or plug any hole as much as possible. Okay, for stiffness, yes, we can improve the sound insulation of the partition through stiffness, but most of the time uh, the, the the effect is at certain frequency range only. Okay, we can do this at low or high frequency range. Okay, for example, if we have something that's flimsy, that means the stiffness is very low, so we can increase the stiffness so that the panel itself will not vibrate and will not contribute to the noise. That's possible. Okay, however, if we move at a high frequency range, now we have uh, natural frequency of the partition itself. Okay, so there's an effect of critical frequency introduced there. So we want to avoid that as well. We don't want uh, the panel to be at resonance. Okay, so if we look at the sound transmission loss versus frequency graph, we'll be seeing something like this. Okay, so we have a mesh law, basically doubling of frequency will increase sound transmission loss by 5 dB or 6 dB, okay, about that range. And then at low frequency range, we have uh, some resonance issue, okay, low frequency resonance, and at high frequency range, we also have some resonance issue. Okay, so we want to ensure that we are within the safe area here. And to increase the performance within this safe area, we have to increase the mass. Okay, so as a rule of thumb, to have a very good insulation, that means to block the sound, uh, we have to have high mass, pretty low stiffness, and also high damping for the partition. All right. Um, if we have discontinuity, sometimes this discontinuity can act as a sound uh, source as well. Okay. For example, if we have a hole, when high frequency sound reach this hole, so this hole will act like a sound source, right? Sometimes discontinuity can be in the form of indirect path. We have what we call as flunking transmission. That means instead of the sound passing through the partition, now the sound is passing through the structure of the building, goes into the upper floor, jump over our partition and goes into the room. Okay, so this uh, continuity is sometimes unavoidable. It's due to the way our building are constructed. We need certain gaps, for example, for ceiling and so on, for ventilation, ducting work, structure joint. So it's there, but we have to minimize it, or we have to plug the hole as much as possible to reduce the effect of this discontinuity, which is affecting the performance of our partition. So we can have something like this. So this is our partition. Instead of reducing the sound through the partition, now the sound is being amplified or being uh, transmitted through holes. These holes can be our hole for electrical plug, electrical conduit, and so on. So the sound can pass through our aircon ventilation system. It can also pass through floor to the adjacent room. Okay, so this kind of noise transmission is also possible. And since we have this other contribution, the overall practical performance of our partition will be reduced. Okay, um, in a room, even though I'm saying that the sound pressure level might not be the same at certain location, but after some time, since we know the sound will be reflecting within this room, you will reach what we call as a steady level or reverberant level. Okay, so initially, if you have a sound source, of course the sound pressure level is very high. Okay, and then it will travel in different direction. Okay, and if we are saying that, okay, we have a fixed amount of absorption and so on, so if we continue to play this or if we continue with the sound source, the sound pressure level will drop at certain level. Okay, this is our reverberant level. It cannot go higher than this because the sound is being absorbed, and if we continue constant sound source here, so the sound pressure level will be constant value. All right, so this constant value is what we call a reverberant sound pressure level, and uh, at this level we can safely say that we are far from the sound source. If we are within this range, we are still within the near field of the sound source. Okay, that means the sound pressure level is changing with respect to distance. After this region, sound pressure level will not be changing with distance. Okay, the value will be about constant anywhere within the room. All right. So in near field or direct field, the sound intensity will be changing with respect to distance and also with respect to directivity factor Q. Okay, where we are with respect to the sound. So sound intensity is given by sound power over 4 pi r squared. So in this case, if we assume that sound is traveling in a sphere times the directivity factor Q. Okay, so this directivity factor Q will change the shape of the sound when it is transmitted. And we know our intensity is equal to sound pressure squared over impedance, uh, the density of the medium times the speed of sound in the medium. Uh, so we can equate these two. If reverberance or diffuse sound field, we know that this intensity is not dependent on distance; it's a constant value. Okay, and if we look at the intensity, it is about quarter of the wave intensity, right? And it is related to pressure to this equation. Okay, so intensity equals to pressure squared over 4 times OC. Right? This is the intensity of sound within the reverberant field. So different situation will change our directivity factor Q. So for example, if we have a free field, the directivity factor Q will be equals to 1. So basically, if Q equals to 1, we have no Q here. So intensity is equals to sound power over propagating area. In this case, 4 pi r squared, which represents the propagating area of this field. So that's the reason why directivity factor for a free field is equals to 1. Okay, it's propagating as a field. On a flat surface, Q now equals to 2. So instead of propagating in a sphere, now the sound is propagating through a half sphere. So that's the reason why Q equals to 2. So if we put Q2 here, so in the end, we'll have intensity equals to W over 2 pi r squared. So basically, the propagating area is half of sphere. So Q will change according to the location of the sound source. Right. So at the junction of two planes, Q equals to 4, at three planes, Q equals to 8. All right. So we can also calculate what we call as directivity index from Q. All right. So directivity index D in dB is equal to 10 log 10 Q. Okay. So what's the use of this directivity index? We can use this directivity index to find the resultant sound pressure level when the sound source is put at certain location, okay, in the space. For example, if we have directivity vector Q equals to 1, D equals to 10 log 10 1, which give us value of 0 here. That means our sound pressure level is equals to the sound source itself plus 0. Obviously, it's the same as the sound source in the free field. All right. So on a flat surface, the relativity factor is, for Q is equals to 2. So D will be equals to 10 log 10 of 2, which means D equals to 3, about 3. Okay. So the sound pressure level is equals to the sound pressure level of the sound source in free field LP plus 3 or plus D. Okay, in this case plus 3 dB. So the sound pressure level will increase by 3 dB due to the reflection of the flat plate. Okay, so we can calculate D from Q for junction of two planes and also junction for three planes. So we can calculate what will be the sound pressure level when we put the sound source in two plane and three plane as well. Okay, so here we have actually 0 dB here, and this is our D for different sound source location. All right. In an enclosure, okay, basically a room can be thought of as an enclosure as well. Uh, we know that if we say enclosure, that means the volume is much smaller compared to a room. Okay? So uh, in the room, again, normally the volume is quite large, so we have uh, a direct as well as river room field in the room. Okay? So uh, we have sound pressure, which comes from the direct field and also from the riverment field. So we can use whatever equation for intensity that we have here for direct field and also for riverment field. Add them up, we have sound pressure squared equals to this term. Okay, so if we want to find the sound pressure level, okay, in terms of level, we take a log of this equation. So we have LP, which is equals to 10 log 10 p squared over p reference squared. Okay, so we have LP here. So using the same reference pressure, we have LW, which is the sound power level, plus 10 log 10 Q over 4 pi r squared plus 4 over r. Okay, so in this case, we can relate sound pressure level with Q as well as the uh, absorption properties in the room. Okay, so what is R? R is our room constant actually. Okay, so uh, we also know that intensity in the river field is 1/4 of the plane wave uh, intensity. All right. Okay, so sound pressure level at the receiving room will depends on the sound power level at the source. It will depends on the distance between source and receiver. So we have R here, okay, and we have room constant in the room or in the enclosure. Okay, and We have Q, which represent the position of the sound source with respect to the room. Okay, it can be at the middle of the room, meaning free field. It can be at the surface of the room. Okay, one plane. Reflection can be at the corner of the room, uh, three plane, or at one side of the wall. So you have two plane for the Q. Okay, so this is how we calculate what will be the sound pressure level in an enclosure or in a room. Okay, if we have both uh, diffuse and also free field sound pressure. All right. Another way to look at this is that this part, this term, represent the geometric spreading of the sound source, okay, how the sound is spreading. And this 4 over R represent the absorption or the different uh, sound loss factor of that particular group. All right. Um, we know that sound pressure level will be the highest at the sound source, and it drops out, and at certain, let's say, this distance, this was sound pressure level. Sound pressure level is the highest at the sound source, and it drops out until it reaches equivalent level. Okay, so at certain area here, okay, or certain distance here, we have the same contribution coming from direct and also referent component of the sound. Okay, so the value is the same. So this distance is what we call as the room radius. Okay, so we can calculate what will be the room radius by equating the density of the direct field with the density of the referent field. So based on this, we can calculate R, which represents the room radius or distance from the sound source, equals to square root of RQ over 16 pi. Okay, so knowing this, we can tell whether the sound pressure level is affected by a direct sound or by the reverberant sound. So if our measurement point is less than R or less than room radius, we know that the bulk of the sound pressure level is coming from the direct sound. So basically the sound is coming directly from the source itself. If we are further away from the room radius, again, our distance larger than room radius, we know that sound pressure level is mainly due to the reflection of the wall, okay, or the reverberant sound field. All right. If we want to apply any noise reduction or treatment in the room, okay, to absorptive material and so on, we should know that it is effective only at reverberant sound field. Okay, we can add absorption to reduce the sound pressure level only at the reverberant sound field, not at the direct sound field. Okay, in the case of direct sound field, the sound is straight away coming from the source itself. Okay, so there's no absorption involved there. Okay, um, so the way sound pressure level changes with distance also depends on uh, the, the type of room that we have. Okay, and this type of room are dictated by the amount of absorption within the room. Okay. If you have a very high level of absorption, we have what goes dead room, basically chamber is a dead room. Okay, absorb all the sound, no sound being reflected or very minimal sound reflection. If we have lots of reflection, uh, we can reach up to uh, reverberant chamber level, or normally you have what we call as light room. There's a lot of reflection, and this reflection will increase the reverberant sound pressure level. Okay, so at this point, we have our R there. Okay, what is R? This guy is our root radius. before this R, we have a direct sound. After this R, we have reverberant sound field. Okay, and in this reverberant sound field is we can reduce by adding absorption. Okay, within this direct sound field, we can only reduce by reducing sound source. In this case, the sound is directly from the source to the receiver, no reflection. And since there's no reflection, uh, there's nothing that can absorb the sound. Okay? And we know that the sound is decaying with distance. If we increase the distance, we have 6 dB doubling. Okay? This is a rule of thumb for uh, sound propagating in space. Okay? If we are saying that we have a linear sound source, then it will not be 3 dB per distance, it will be it will not be 6 dB per distance, but 3 dB per distance. But generally, we're assuming that we have a free field sound in space, so it will be 6 dB per doubling distance. Alright. We can also calculate the sound pressure level using charts. Okay? So, for example, we have something like this. We have the relationship between sound pressure level and sound power level. Okay, sound pressure level, sound power level, and then we have here what we call room volume. Okay, room volume will dictate the revolution time, and of course, this will also dictate the room constant. Okay, and then we have the relationship between directivity factor Q and also distance from the sound source. So we can use this to calculate the sound pressure level at the receiver. Or I normally use equation to do that, much simpler. Okay, so for example, if you have a room with a dimension of 8 meter long, 6 meter wide, and 4 meter high, and this room has a surface with uh, following absorption coefficient: floor has alpha equals to 0.02, wall 0.04, and ceiling 0.1, and we told that RT for the room is 3 seconds. If you have an omnidirectional sound power of 0.05 watt at the center of the room, what will be the room constant? Okay. And then we want to calculate what will be the radius, the sound pressure level, and the direct and total sound pressure level for one to be the distance from the sound source. Alright, so in this case, we have to calculate what will be the surface area of the room, the volume of the room, and then we can calculate what is our room constant and also our average absorption coefficient. Okay. So sound power level from in this case we have sound power of equals to 0.05 watt. So 0.05 watt divided by reference sound power level 10 minus 12 watt. So we have 107 dB as our sound power level. The area is equals to 10.2 meter square. Our average absorption equals to 0.05. Okay, and sorry, this A is not area, is absorption is equals to 10.2. Alpha average absorption coefficient equals to 0.05, and surface area equals to 208 meter square. So our room constant is equals to 208 surface area times average absorption coefficient divided by 1 minus average absorption coefficient. So we have 10.9 meter square. And the reverberant sound pressure level equals to sound power level plus 10 log 10 4 over our room constant, which is given by this guy here. At 1 meter distance, we know that our direct sound pressure level will be equals to 107 plus minus 20 log 1 minus 11. Okay, where we got this, this is from what is that? Okay, this one is relating some pressure level with some power, and dependent on the location of the sound power with the surface. Okay. So here we have 20 log 1. Okay, the 1 represents distance, and then here we have minus 11. Okay, this minus 11 it depends on where the sound source is located. Okay. In this case, it is located at the center of the room, so that's the reason why we have 11 here. If it is located on the surface of the room, then it's not 11, it's probably 8. Okay. So we are using equation that we have seen before. Uh, at 1 meter distance, the total submersion level will be a sum of uh, 110, okay, plus 10 log 10, uh, 1 minus this value. Okay, this is 1 over 4 pi r squared plus 4 over 10.9. 10.9 is our LC. Okay, so this will give us 103.5 dB. 1 is our Q actually, okay, for this particular example. So we can calculate what based on pressure level at 2 meter distance, and also the room quotient. Room quotient will not depends on the distance. Okay, sorry, room radius is not dependent on distance. Okay, so we have 0.48 46 meter as a room radius for this particular uh, room. Alright, so based on this, where we are at 1 meter distance and at 2 meter distance, basically we are not at the direct field, we are in reference field, because this is 0.4 meter. At one distance we are already at reference field. Okay, any questions so far? Okay, if there's no question, I will stop the class here. You can look again at the slide, and we can discuss again if there's something that you don't understand next week. Okay, so that's it for today. um, Take care of yourself. Have a nice weekend.
Thank you, Doctor.